Hello again. Yeah, a couple of years ago my daughter went on a school residential camping. My daughter was required to take her own torch if they needed light in the evening, if they didn't like the dark. So I thought rather than give her a conventional torch and a boatload of batteries, I thought I'd actually build one of the famous Joule feeds. Basically all they are is like a self-oscillating voltage booster. A clever, nifty bits of kit, because what it means is that you could put like a AA battery in there and it just lasts for weeks. You know, the circuit just keep running until it's discharged the battery completely, rather than most electronic devices that a typical AA you'd be dead at a volt and you've thrown it away. So there you go. So I thought what I'd do today is I'd just do a video on how these things actually work. I know there's a lot of information on the internet how they work, but some of them are a bit hazy. So I thought what I'd like to do is show everyone exactly how they work. I'm going to assume that the person who's watching this is a beginner that really hasn't got a clue how it works whatsoever. So just have a quick walkthrough of the actual physical thing. So basically all it consists of is an NPN transistor. Got the LED there, I'm using a 10mm, and a ferrite toroid wound with a copper coil wrapped around it. I think there's about 20 turns on there, and just a 1k resistor, that's it. And we've got a little switch there, and obviously the battery in its casing, and just a little piece of wire there I put. No, it's got nothing to do with it anyway. So what I'd like to do first, I'd just like to walk you through each and every component, how they work. I want to show you how the NPN transistor works, how the coil works, and what its purpose is in the circuit. And we'll have a little chat about the LED as well. So what I'm going to do now is just actually scribble down the schematic for you, and we go through each and every component and show how they work. So I'll do that now and I'll be back very shortly. Yeah, so I scribbled down the schematic. It's an extremely simple circuit, and then on the other hand it's an extremely difficult circuit to get your head round how it works. So what I'm going to do, I want to go through each and every component and try and explain exactly how they work. So what should we do? Should we start on the easy ones or the hard ones? I think what we do is start on the easy ones. So what I'm going to do now, I'm going to talk about the transistor, and I'm going to assume again that you ain't got a clue really how they work. So that's what we're going to do very shortly, but before then I'll just point out I've tried to list everything what they are. Like obviously that's the 1k resistor in the schematic, this is a coil, we'll talk about that later. This is a transistor, an NPN type, and this is the LED, and obviously we've got the supply here which I've just put as 1 volt. So there you go. So what we do now then, we just settle down and have a chat about the transistor. Then once you've got all these components in your head and you've got an idea how they work, when I actually walk you through this circuit how it works, it should become pretty simple for you to digest and understand how it works. And then at the end I'll connect the oscilloscope to it, and we'll have a chat about the waveforms as well, which will even make it more sense. Okay, so the NPN transistor. So let's talk about the transistor. Right, transistors come in 2 flavours. They come in NPN and PNP. We're just going to be talking about the NPN transistor today because that's the transistor we use in our circuit. So this is the circuit symbol of the NPN transistor. So we've got the collector, which is usually at the a positive voltage, a higher voltage than that, usually the supply voltage to say. We've got the emitter, which you'd usually have at ground. And then you've got the base, which takes a small current to operate it. So transistors have usually got two forms of operation. Excuse me. You can use them as a switch or you can use them as an amplifier. In our circuit it's going to be used as a switch. So let's have a chat about that. So if you can imagine we've got a switch in here and it's controlled by the base. And usually the base to operate the switch from a range where it's nearly closed, fully closed, you're looking at 0.5 volts to 0.75 into saturation. So if you can imagine a switch here, you can see that. Yeah, so if you can imagine a switch there and we're controlling it by a voltage here. So we put 0.5 volts in there, the switch would close, not fully closed, but close enough for current to run through this side of the circuit. And then if you can imagine we have put into 0.75 volts in, which would send the transistor into saturation mode. Whenever you hear that, it means that the switch is fully on and you've basically got a short between these two. So if you can keep that in mind, and usually on the base we'd have to have a current limiting resistor in there, because you can just destroy the transistor if you have too much current running through there. So if you keep in mind we can control the switch by a small amount of current and voltage running through here, which you go from the base to emitter. And I think that's all you need to know for the time being. All you need to know is that we're controlling it as a switch. So we put 0.5 volts in there, the switch is not quite closed, but it still lets a certain amount of current through. And then if the voltage is raised to say 0.65 to 0.75 volts, I put it into saturation mode where the switch is fully on. So if you can keep that in mind, we move on to the next component. And I think the next component we look at the coil. This could be a bit more lengthy because they're not quite as simple as a transistor. Okay. Right, now let's talk about the coil. Let's talk about the coil in the circuit now, how that works. Right, where do we start on this? So, any conductor that is made into a coil and current passed through it creates a magnetic field. So let's draw some. Let's have a look at this. So if you can imagine a coil here, and we attach it to a battery. Excuse the drawing, I'm no artiste. So we attach it to a battery, so that's a negative, that's a positive. So we can connect that coil to a battery, it will create a magnetic field which would look something along the lines of like this. So if you can imagine these as the magnetic fields, something like that. So this side as well, and here, and at the same time you'd have little fields coming out here as well. And these have poles, like you have north, south, just like a magnet. Now typically be running like that. I'm not going to get too deep into it. Obviously the south will be running that way. Right. So this is a magnetic field and the strength of it is measured like magnetic flux. I'm not going to go into it too deep, but all you need to know is if we was to connect a battery to a coil, it would create a magnetic field. Just like the permanent magnet that's permanently magnetised, the coil would do exactly the same thing when we run a current through it. Right, the next key bit of information is something that you could keep in your mind. If I was to disconnect the supply from that magnetic field would collapse, and as it collapses and cuts through the fields cut through the conductor, it will induce a current through this coil, through the circuit, usually in the opposite direction to the current of the battery, which is conventional current flow would be that way, but obviously electron current flow would be running that way. So if we had current running through this way with the battery, through the coil, it would create a magnetic field, disconnect the supply, the field would collapse and cut through the conductor, and as it collapsed it would induce a current the opposite way. So what I think I'm going to do now, I'm going to make a small little coil up, and it's very similar to this, just to demonstrate practically what I mean with this drawing. So I'll set this up now. What I'll do, I think I'll pause the video because you don't want to see me scratching about winding coils and whatnot. So I'll see you in a minute. Yeah, so I've wound the coil. Basically what I've got, I've got one of my iron routers there, and I've just wrapped about 30 turns of coil around it. Obviously I've incorporated a switch in here just to switch it on and off, and I've got 1 volt running through it from my power supply. I couldn't be bothered to current limit it, so I've just lowered the voltage just so we know we don't have too much of a current through it and catch anything on fire. So what I want to demonstrate here is what I was talking about earlier on paper about the magnetic fields that are set up once we got current running through a coil through the iron core. You would still get magnetic fields if you just had the coil there, but it just increases the actual magnetic lines of flux when you've actually got an iron core running through it. It sets up a bit of hysteresis in there and just concentrates it more in one place. So anyway, enough of me babbling on, let's just demonstrate. So if I'm putting 1 volt through it now, as you can see, it's there's no current running through at the moment, it's not acting as a magnet. So if we was to put switch this switch on, we'd induce, there you go, look. So basically we got DC voltage running through the coil, which has created us a magnet. So we let go, on again, and let it go. When we let it go, and when these magnetic lines of flux collapse, and they will actually send a current through this back current through this actually coil. So what I'm going to do now, I'm just going to show you on the oscilloscope what I mean in that. So if I just, so what I'm going to do, I'm going to set my oscilloscope up just to capture the magnetic lines of flux collapsing as I push the button on, and then when I release it, you'll see on the scope that it creates a quite large negative voltage. So if I can set this up, so I'll set this up there, I'll put that onto the ground, and I'll set the oscilloscope up here. Should I single capture it or normal? Let's try on single first. So I'll just show you the oscilloscope. Probably won't get us all in. Let's see if we can. Then we'll zoom into the oscilloscope then. So if I push the button down, Now we've got a magnetic field running through that. When I let it go, it should collapse and create a negative voltage. And that's what we've just captured on the oscilloscope. So we zoom in. There you go. Right, so we're looking at 25 volts per division here. So you're looking at, there's about 70, well it goes down actually, you're probably looking at a negative 75 volts, and that voltage was induced when the magnetic lines of flux collapsed and cut through the coil. So if you can keep that in mind, what I've just told you about how the coil works, how the magnetic lines of flux collapse, it creates an induced voltage through the coil. So I hope that you understood that. I tried to explain it best I could, but if you can understand that and taking it all in, we'll have a walk through the circuit in a minute, and you should have a very good understanding how it works once I explain what's going on. Okay, see you in a minute. Right, before we go hopping on the back of an electron, I just need to explain a few important concepts before we delve into this circuit. Right, if you didn't know, LEDs have a voltage drop, meaning that they require a certain voltage before they start conducting. In this particular one, the white LED, you're probably looking at around 3 volts. So if I was to whack this across this battery here, it won't conduct because the battery is a dead battery. It's probably about 0.8 volts in it. So as you can see with the Joule thief, not a problem because it's designed to do that, isn't it? Right, and another important concept, very important concept, is the actual winding that we're looking at. You probably noticed the dots here. It's a dot convention. Basically this is telling us that one side of the coil is wound clockwise and the other one's round anti-clockwise, and this is very important. What this means is when the magnetic flux collapses on them, you're going to have a signal that's going to be 180 degrees out of phase. So if we look at like the secondary winding here, when the magnetic flux collapses, that will go negative, and the primary side, that's going to be positive, and that's very important for the circuit to work. So if you can fix that in your head while we're running through the circuit, it'll make a bit more sense. So now it's time for us to have a look at this and see if we can understand how it works. So we've just switched the battery on. We've got a small amount of current, 0.5 volts or whatever the battery is, running through the secondary coil, tickling the base of the transistor. And at this point the transistor switches on slightly, meaning that the switch is closing slightly, and allows a larger amount of current to run through the primary down to ground. It can't run through the LED because the voltage is not there yet. And these magnetic lines of flux cut through the secondary coil in that direction, creating a little bit more voltage, and that extra voltage turns the transistor into saturation mode, which means it's fully on. There's a short, basically the coil's across the battery. At this point we got the maximum magnetic lines of fluxes set up in both sides of the coil. And as you can pause for a moment and think that it's set up, and at this moment this side of the coil starts dissipating through the 1K resistor, switching the transistor off. And it's at this point where all the magnetic lines of flux collapse, and this collapsing current, positive current, runs through the LED, and that is the actual cycle. So we run through it again. So we have a small amount of current running through the secondary side of the coil, tickling the base of the transistor, switches the transistor on slightly, which creates lines of magnetic flux through here from the primary, and that primary lines cut into the secondary, creating a little bit more voltage to turn the transistor on fully into saturation mode. And at this point we've got maximum magnetic lines of flux set up into the circuit. And as the current this side starts dissipating away through the 1K resistor until the transistor turns off, the magnetic fluxes collapse and we have a negative voltage through the base, which means that it can't conduct, and the only place that the positive current can run is through the LED, and it just repeat that cycle. I hope you understood that. So now what I'd like to do is connect the oscilloscope to the actual circuit. So what I'm going to do, I'm going to have channel 1 of my oscilloscope just here, and I'm going to put channel 2 just here, and hopefully what I've just explained you'll be able to see on the actual oscilloscope. So what I'm going to do now, I'm going to pause and just hook my leads up, and I'll be back shortly. So I've hooked the system up to the oscilloscope now, and I'll just run through the channels. You got channel 1 is the yellow, channel 2 is the blue. So if we'll just go back down onto the schematic for you, and we can see there. Look, so we've got channel 2, which is effectively the base of the transistor. So if you can think of that, and channel 1 is the primary side, which is the LED side. So if we go back here, and you should be able to understand what's going on in a fashion. So as you can see, this point here is when the circuit initially switches on. So if you take a look at the blue channel, you can see I've got 2 volts per division. You can see that it's actually at 2 volts. And channel 1 is the primary side, which is the LED side, and that's basically floating just below ground. And this point here, if we can imagine this point here, is when the transistor is in saturation mode, and it's like basically frozen in time, waiting for current to actually dissipate. So it's low, so the voltage is low enough for the transistor to switch off. And it's at this point where the actual LED lights up. So we can see on channel 1, the LED side, we have this initial spike of current which actually dissipates through the LED until we're back to square one again when the battery takes over and starts the process again. And as I was saying, it's important with the dot convention here. Look, you can see whatever happens on channel 1, channel 2 basically is doing the polar opposite. And that's important, because if it did the same as channel 1, the transistor would never switch off, would it? So as you can see it rolling off here, this is where the actual that initial magnetic flux starts to dissipate through the 1K resistor, through the actual transistor, and when it reaches a point when it switches off, where the magic happens. So there you go, that's one cycle there. And as you can see, I don't know if you can see it from here, you can see that the actual frequency of my system is around it's around 52 kilohertz, 52,000 cycles a second. So there you have it. I hope you understood that. Sometimes I find it hard to actually articulate what's in my mind, but hopefully you can actually understand what I understand, and I hope you enjoyed the video. I hope I didn't waffle on too much. It's been going on a bit now. Yeah, we're looking at around half an hour. So thank you very much for watching. If you've reached this point, I hope it was some use of you, and have a good day, and I'll catch you again later. Thank you.